be able to present to an IEEE chapter. Certainly, I've had a lot of mentors throughout the years. As mentioned, I've been a member of IEEE for 34 years, so I really couldn't turn down the invitation, even though one of our principal engineers who just passed away a few months ago had been doing these webinars almost every week, all through COVID. And Mr. Craig Hartman was a real industry specialist that started with Westinghouse back in the 70s and had an extreme amount of knowledge. And we pulled some of his slides, but primarily put this together more from the perspective of a history of application and compatibility issues that we've experienced that I hope will be of interest to the group here. What we'd like to talk about today primarily are the compatibility issues that we've seen associated with VFD and motor systems. And then we've got a section where we'll go through what we kind of, from a historical standpoint, see as some of the top considerations in applying and specifying and in servicing and maintaining the VFD systems. I'd like to maybe start off with getting a little perspective, and maybe Sajal can monitor maybe a chat room to know what experience you've had, or if you believe you've seen applications or projects where VFDs have caused motor damage, number one, or if VFDs have had a negative effect on the electrical environment. So if it's possible, Sajal, could you maybe kind of monitor the chat? I think we have chat capability, don't we?
Yeah. If anyone wants to put it on the chat or even talk right now quickly, it's open floor for us.
Yeah, I'll monitor the chat also as well, and then we could just read the questions out loud as they come up.
Yeah.
Great. Yeah, I'd love to be able to talk from the perspective of some things that you might have seen and hopefully make the presentation more relevant that way. So I'm going to start off with a couple of slides that are a little bit about our background and how we're seeing this particular industry of applying motors and drives. Energy Management Corporation was founded in 1979, still a small company with 120 or so employees in about 7 or 8 states. Our specialty is in electrical motors, drives, variable AC drives, not so much DC drives anymore nowadays, and standby generators. And so those particular products are a unique combination that do present certain challenges in compatibility. The second slide, we typically look at about everything we try to do from the perspective of safety, reliability, and energy efficiency. We're not a typical distributor, even though we stock over 3,000 drives throughout our different facilities, and we stock a large inventory of motors and even power quality equipment like line reactors and filters. So some individuals look at it as a distributor. We also have facilities like in our Los Angeles Pomona facility. We do have a motor repair, motor reloading facility where we repair motors there up to about 10. We have 10-ton cranes there. In our Rock Springs facility, we go up to 25 tons. So we work on very large machines, and we have field services such as vibration analysis, and we did kind of perfect, I think, what we call the inverter duty rewind, probably about 20 years ago. We do engineering studies. We do get involved in arc flash studies and harmonic analysis. And then we have an integration side where we are a UL 508 integration facility. We have field service engineers that do the commissioning and startup and so forth. So that's how our company, Energy Management Corporation, comes to the market with that kind of perspective. Because you can buy a drive or a motor almost anywhere if you've got a part number to take to WW Grainger. But as you well know, there's more issues associated with that, and that's what we hope to cover a little bit more today. Briefly on those 3 aspects of safety, reliability, and energy efficiency. An example of that might be you often see drives just mounted as what we call a chassis drive on a wall, or a chassis and a disconnect, where we tend to advocate more a packaged approach like you see here. And we'll talk about some of those kinds of things. Obviously, when that drive is in a metallic enclosure, you've got EMI, RFI reduced. You've got a more safe product, but you've got the ability to add products or components that might be helpful when you run into compatibility issues. From a reliability standpoint, here you see on the right slide a crusher application that is in a very hostile environment. And in this particular one, we do have a significant amount of ventilation and a filter system that gets changed frequently. And this is one of the systems where we also have remote monitoring capability, so the user can actually monitor this whole system from an iPad or whatever. So these are some examples of kind of the systems that we look at the application and then try to design in from the ground up what is going to make that particular system and process more reliable. And then the last one, I don't think I need to speak too much about energy efficiency. Everyone nowadays specifies drives in any kind of flow types of loads, knowing that with following the affinity laws, the power is going to be reduced by the cube of the speed as you change the pump curve or the fan curve. So that's pretty well known nowadays. But if there are any questions on those, we can address those later. So what we're going to focus on here for the next 10 or 15 minutes are compatibility issues between the VFD, the electrical system, and the electrical machine or machines. You could have multiple machines on one single drive even. And look at it from a electrical distribution standpoint. You've got the utility here, which certainly has somewhat to say regarding non-linear loads coming back into them. That's usually measured with the utility transformer or the point of common coupling on the primary side. So we'll talk about each of these points where there could be an interaction of compatibility challenges. Certainly the generator, we have a lot of experience with generator compatibility issues. We didn't list the automatic transfer switch here, but any kind of control could have challenges. As a matter of fact, I remember one project has probably been 20 years ago in a power plant where I think it was VFDs that were installed on their cranes. And whenever they ran them, they had some of their water, I guess these might have been feed water pumps to their cooling towers, but the valves were chattering. And come to find out that because the output of that drive in a crane was on a festoon, it was radiating noise. And every time that would happen, they would have their valve and control system go crazy. So certainly we're not going to talk a lot about controls today. This is more the power side of things, but those issues do exist. Circuit breakers, you know that the waveform can have a higher peak and sometimes can have nuisance circuit breaker issues. And then the VFD itself and the cable to the VFD and the motor are all things we hope to touch on a little bit as they relate to once you've added this device, that VFD, what you might need to know that could be affected in other parts of the system. And I'd have to say that I give the presentation like this a little bit with a little bit of intrepidation because I don't want to insinuate drives are problematic. You know, drives are very commonplace and very commonly installed nowadays. And the problems we're talking about are not the norm. If we install a drive nowadays, there's probably very little chance of DVDT issues with inverter duty motors and so forth. But we've encountered problems in all of these areas, and we'd like to discuss that just a little bit. So my first question, I don't know, did we get any comments on experiences of VFDs believed to have caused damage to motors, machines?
Yeah, we did actually from Keen Matsuda. He said he has seen 6-pulse VFDs cause damage to motor shaft with fluting and also damage to first phase winding turns from reflected waves.
Great. Those are topics we can address today. So I'll make sure we've included that here. Any others?
Yeah. That's the only thing. But I would
Okay.
like to know what is fluting means. I had never heard the term before.
Well, just hold on. I've got a slide that I've got labeled fluting. So I think we can address that one. So let's move on. To understand the issues, and particularly those that, was it Hamid that posed those experiences?
Oh, no, that was Mr. Matsuda.
Mr. Matsuda, okay. So we're going to start then with the output section of the VFD. A VFD typically, when you look at the topology, consists of a converter section, a DC bus filter capacitor section with control. And then the output is an inverter, inverting AC to DC. And the typical waveform is what you see here in the bottom. I hope that's coming through clear enough, where it's a typical PWM waveform, where the longer the pulse is on, the more voltage is going to be seen by the motor, and it's going to synthesize an AC sine wave from a current standpoint. From a voltage standpoint, it's just a lot of pulses. Is that pretty clear from that slide? Can you see that?
Yep.
You're probably already familiar with PWM waveforms. So the standard that deals with the two issues that Mr. Masuda brought up are the NEMA MG1 standards that were there've been 3 different dates, I think, of standards updates. The last one was approved in 2018. And we think of NEMA MG1 as Part 30 and Part 31. Part 30 is typical general purpose machines that could be used with VFD control. And Part 31 deals more with actual, there's no term inverter duty motors in the NEMA MG1, but inverter fed motors. So inverter duty is kind of an industry term that is trying to address this. So a couple of the points, when you look at the, especially when you think about the term inverter duty, it could mean a lot of different things to a lot of different people. The torque derating from a cooling standpoint could be very detrimental if you have a constant torque load like a conveyor and put a motor on that's only rated for maybe a 4-to-1 ratio, and you're now turning it down 10-to-1 ratio, you're going to run into cooling problems. And so that's addressed in 30.2.2.2 in cooling issues associated with reduced speed applications with inverters. And then for those motors, they're saying basically, if you can make sure that a motor that is a less than 600 volt class motor, so our 480 volt motors, under medium voltage motors, that if you can have the voltage stress or the waveform that the motor sees less than 1 kilovolt and more than 2 microseconds of rise time, you should be okay. There should not be an issue. When you go to the Part 31, you get a little bit more specific, saying that there still is there's temperature rise associated with variable speed duty. And just as a side note, when we apply an inverter on like a pump or a fan, the variable torque nature of that reduces the load so much that we don't worry about turn down ratios or those kinds of things. As a matter of fact, we see the skin temperature of a typical machine go down when the speed is reduced, because you're reducing it by the cube of the speed, typically the power plus losses. The next, and the 2 parts I think that we're addressing here now are these voltage spikes. Again, under the 600 volt and less motors, they're suggesting that the motor is rated at 3.1 times the rated voltage. So with a 460 volt motor, you're looking at 1400 and some volts. 480 volt motor, some look at it as a 480 volt motor, and that would be 1488. It's a little different than you might have heard in the past, because the standard started with a 1600 volt requirement. And so I've always thought, those motors had to be able to withstand a 1600 volt peak. And of course, the rise time is also able to come down. You have to have greater than a 0.1 microsecond rise time and be free of partial discharge. And if any of those terms are not familiar, we can talk about those more. And then the second part that I think is of high interest from the question is the shaft voltages and bearing currents, basically shaft currents that are addressed in 41.4.3. And if you want to get this exact standard, this is one of those standards that I'm surprised you can log into NEMA.org and actually download this electronic version for free, rather than paying the $659 for a hard copy. So that's a lot in one slide. Also part of NEMA MG1 is this rise time. The way they measure rise time is from a stable voltage of 10% to 90%. And they're looking for the slope of that to measure the rise time to be below that 0.1 microsecond. And of course, the peak voltage is this. Now you remember from that waveform, and I think I probably got another slide that might show this more. The reason this is happening is because of the reflected wave phenomena, that when you have an impedance mismatch, you're sending one of those PWM pulses down the conductor, and it's going to have capacitive coupling. It's going to see inductances, and in certain situations, it's going to be doubled or even 4 times in a reflection back to the motor. I don't have a slide of a ringing wave, but I think everyone can kind of visualize this pulse that you're sending down a transmission line, and it's bouncing back at you at a higher than initial rate. Typically in the past, the thing that has been done has been applying a DVD-T filter, or actually, I'd go back maybe over 20 years ago, Alan Bradley and others had a filter, and we actually built some called a motor termination filter, where you're trying to match that impedance to suppress that waveform. But a DVD-T filter is basically an inductor with a resistive network, and they're relatively expensive, and we saw a lot of those being put in specifications when it really was not necessarily necessary. And it's a somewhat of an expensive device, a lot more expensive devices. And some of the manufacturer's recommendations is when it was over 100 feet. Well, what I'm showing here is that an output reactor, and probably not just any output reactor, can also, in the right situation, do a substantially mitigate some of this phenomena in certain applications. So we look at this as kind of a stepped approach. You've got an output reactor, a DVD-T filter, and then a full sine wave filter. A good place for a sine wave filter, we probably would not install a deep well submersible pump without an output sine wave filter. It's just too expensive to pull that pump out of the hole for a DVD-T failure. But years ago, we ran 1,000 feet of conductor around our warehouse and the offices and trying to measure some of this effect. And we saw in some situations where a reactor itself actually increased that DVD-T. Again, it's an impedance mismatch. And so our recommendation, or from our experience right now, would be that, and when I say not just any reactor, because typical reactors can't handle the waveforms of harmonics, so they're usually rated with being able to handle a certain frequency spectrum. The one that we're using nowadays is imported from Germany, and it's a polygap. So they've distributed the air gap on the core of this reactor, and we found it to be a phenomenal performing reactor. And so we would use that kind of a reactor probably easily up past 500 feet of cable length. When we start approaching 1,000 feet, we're going to turn to a DVD-T filter. And then when we have, we just did a project last year at a ski resort that drilled a hole from the top of the mountain all the way down to the aquifer, which is, I think, 2,000 feet. And the sine wave filter was the only option there. So here's a little bit of background, or a little bit of, here's our typical PWM waveform. You could call that a lab waveform, but it's also not atypical in most installations. But this one you see right here is just a data center with only maybe 200 or 300 feet of cable. It surprised us to see that kind of waveform. Now recognize that when you look at these divisions of 500 volts per division, we're looking at about 650 to 750 volts peak on the DC bus. These peaks are going well over 12, maybe 1,300. And the customer originally called us because they had a motor failure. And because we do root cause analysis on machines, we were able to determine that that was an end-turn failure. That's a classic DVD-T failures on that initial coil turn where the voltage potential is the highest. And it happened to be on an inverter duty motor, by the way. So all motors are not perfect. And if there is a flaw in a motor, and we particularly were concerned at from a rewind standpoint, how do we do an inverter duty rewind that's going to survive this phenomena? We find that we can typically do a better job than the manufacturer when we use a automatic winding machine, so we have no coil overlap, when we do a strong VPI or vacuum pressure impregnation, and we have a good structure in tying down the coils. That is what creates an inverter duty rewind for us. This graph over here on the top right is with a filter. That filter actually is that reactor. It's not a DVDT filter, but the performance you can see is down under that 1,000 volts, and it performed as well. And that was a 300 foot and probably maybe half the cost of that DVDT filter. And of course, the sine wave filter is the Cadillac, but also at a Cadillac price. Bearing currents, and hopefully I can move along fast enough here.
Quick question.
Yes, go ahead.
On the scope view without filter, did you get to measure the actual harmonic distortion?
On the output waveform, we did not measure the harmonic distortion. We would have to have a meter that would be, I guess we could approximate that, but it usually takes a very accurate instrument to measure harmonic distortion on a PWM waveform. And we haven't, we've experimented with that a little bit, but those graphs certainly did not have a harmonic content. Usually the harmonic content from a current standpoint is not too bad. You know, it might be less than 5%, but that brings up another question. When you apply an inverter on a motor, most manufacturers will say that you don't have to derate the motor necessarily, but you do need to give up some of the service factor.
Right.
Mm-hmm. There is a little bit of heating there. Yeah. So thank you for the question. Moving on to the bearing currents. That's the same waveform traveling, you know, in that conductor, but the capacitive coupling, and there's no symmetry between the ground and the individual conductors. So what you'll find is that this bearing is traveling on a film of oil, and the only insulation between that is that film of oil. And I think I need to move a little faster here. But here we see our fluting example. That's the outcome of multiple electrostatic discharges over a period of time. And that is sometimes referred to as fluting. And I've heard that some say it actually sounds sometimes like a flute when you get that far, but that's the typical fluting effect. This is from, on our motor electrical machine rebuilds, it's common practice for us now to cut apart every single bearing. So that obviously is not done by a lot of facilities, but we've seen enough of this now that we always cut the bearing and look for this. It's not nearly as prevalent in the early stages. This is just a graph that shows you can actually measure the shaft voltages by putting like a fiber brush on the shaft and then on ground. And we do have some graphs of that. And this is I think 1,000 horsepower vertical motor. So here's what you'd see when you take that, when you have an oscilloscope. You have to have an oscilloscope to capture these waveforms. But you see a buildup of voltage and then a complete discharge of voltage. That's how you know that you've got this bearing current issue, that you see that rapid and overshoot on the collapse of that. And that's what it starts to cause that electrostatic, the pitting that we'll see in a few others. Here's a couple of other oscilloscope graphs from, I think this one might have even been that, no, this wasn't the data set. This was another vertical hollow shaft, which seemed to have more propensity to this sometimes. You can see that this built up a little bit longer until it hit that. This was a lot longer. This was a very short one, but those classic waveforms from an oscilloscope, and what you do is you see that ring on your oscilloscope, and you've got to now expand in on that initial rise time. And this again, well, I was going to say that the rise time is associated with DVDT, but really this is your shaft voltage, so it's not really associated with the rise of that first coil of the electrical winding.
A question quickly.
Yes.
Is this only when you have VFD, or it can happen in a regular motor without a VFD too?
That's a great question. That's a great question. You know, actually, partial discharge and bearing currents is not a new phenomenon with VFDs.
Correct.
Those that have been in the transmission industry with large generators find that they've been putting some kind of mitigation techniques on those large machines, let's say like a 2 or 3 megawatt machine, for probably 100 years. And the reason it occurs in those situations is because of eccentricity in the rotor. It'll cause the same kind of issue. So you can see here under a microscope, you can see these very small. It's just like a like electrostatic discharge. Well, you know, like a machine that's actually cutting or something. It's little pits that it's building up, and then you can see the magnification until it ends up. If there's a bearing problem that we catch on we typically use SPM instruments for our vibration analysis, which use a shock pulse method, which allows to detect some of these failures a little bit earlier than a typical accelerometer. But this is where it ends up, and you can hear the audible noise for sure at this point. And of course, it can be both in the inner race and the outer race. Now, of course, if someone lets us go too long, the bearing will fail, the rotor may crash into the winding, and then you have a total catastrophic failure. So probably, I don't remember the percentage we figure, but the majority of electrical motor failures are mechanical failures, but many of them cascade into electrical failures.
Quick question. Is this the static charge? Is it a DC current discharge?
Oh, well, when you look at the waveform, there's a ring to it to begin with, and that rise, I guess you could say, would be more of a. I'm trying to think of how to exactly answer that, because if you think of a capacitor coupling to a conductor in a shield that you're trying to say prevent noise in a shield, it's that coupling effect. So I think from my perspective, it ends up being more of a DC voltage, but there's certainly AC components in it. And another thing that might be interesting is we typically think of anything below 5 volts. And that when you go back and look at the NEMA MG1, they'll say there's not enough conclusive evidence to really give a definite recommendation what to do, because applications vary so much. There's so much variety to it. But they say right in MG1, NEMA MG1, that they are seeing shaft voltages from 10 volts to 40 volts. And those clearly are causing damage. When we do our testing, we typically consider something under 5 volts as not being consequential to what we'd expect to be a lot of damage. Thanks for the question. As I'm just talking now about the output of the drive, we've got the input to talk about also. We have been, I guess when these things first came out, I'm sure you've heard of taking regular carbon brushes and having them ride on the shaft of the motor. That's what they did certainly in the old days with generators. Now this technology of having this fiber strands in a ring that are very robust, and as long as you have it in a location where it doesn't get caked with oil and dirt, we typically like to put them inside the motor rather than outside the motor, but you can do either one if you've got an environment for it. I don't know if it shows up very well, but these are thousands and thousands of little fibers. And so they're riding on the shaft, and they're all at different heights. We find these to do an extremely good job. But in the early days of us experimenting with it, and we stock hundreds of these now, and many of our customers just say, I don't want to deal with taking that motor out, even if it's on just a supply fan in a commercial installation. Matter of fact, that's some of the worst ones is in fan walls. In fan walls, we see probably a significant amount of the bearing currents. And remind me to, if the question doesn't come up, to explain where we see most of the DVDT challenges. But just installing what we call a shaft grounding ring does a really good job, except that when you get into larger machines approaching over 100, and by the time you're at 200, you really have to make sure you're also insulating one end, and either with a ceramic bearing or a ceramic coated journal. And in the NEMA MG1, it does talk about even having 2 insulated bearings. But that shaft current is going to come out somewhere if it doesn't go to ground. So it could come out through your pump bearing or through some other location that's connected to that shaft. And please, we've got about I think some time allocated at the end for other questions. So I know I'm going fast, but we only have an hour here, and I want to cover broadly the all these application and compatibility issues. So I'm going to turn this portion over to Sid to take on now, looking at from the input of the inverter.
Thank you, sir, and I thank you guys for giving this opportunity to talk on this topic. So the question is, do VFDs affect the electrical environment? I don't have an answer for now, but let's see what we have got. In order to understand what happens when we use a VFD in electrical system, we have to understand VFD topology first. So getting into the VFD topology, so we see that, okay. So here we have AC to DC converter, a filter section where we have a DC bus, and then we have a DC to AC converter, which is inverter. So what is happening here is AC being converted to DC, and DC is being converted to AC back again. So so here you can see that we have a graph where we have voltage and current of a typical 6-pulse VFD input waveform with load on it. So that's how current waveform looks like. So this topology reminds us of UPS systems, where we do have similar sections of rectifier, inverter, and DC bus, but DC bus charging the batteries. So I want to say here that most VFD, most variable frequency drives and UPS systems utilize 6-pulse rectifier configuration. So that is typically seen configuration, but we do have different configurations too. So when we have such configuration, we see solid state power devices there, of course, diodes typically, and diodes during the rectification process, because of commutation notching, creates ringing frequencies, which I call harmonics. Well, harmonics. So harmonics are nothing but just frequencies other than fundamental frequencies. So if you say second harmonic or third harmonic, as you can see on the screen, they are just like multiples of the fundamental frequency, which is 60 hertz. So that's a general definition of harmonics. You guys know that. So what I typically refer harmonics is as electrical system pollution. So these harmonic noises propagate into the electrical grid and pollute their systems. So how does a voltage waveform look like if we have harmonics of third and fifth that you can see on the screen? But the blue waveform that you see are the one that you see on the oscilloscope. So, and this distortion can be broken into individual harmonics, and that is done by the Fourier transforms, of course, and that is what we refer to total harmonic distortion or of voltage or current. So what that means is, for example, total harmonic voltage distortion is the total effect of all voltage harmonics on the fundamental. So that's what total harmonic distortion means. So getting into the current harmonics. So this is how current harmonic looks like, that you see in the blue color. So if we have a single phase input, that's how this is how the harmonics look like. But if we have a 3-phase input for the VFD, this is how it looks like. So the high current peaks that you're seeing are the result of the capacitor discharge on the DC link of the VFD. So and we have to note that the diodes allow the DC bus capacitor to charge whenever the voltage on the incoming sine wave exceeds the voltage on the DC bus. Thus, we get a large surge in current, and that's what you see here as a current peak. So So, and these are the typical harmonics that you see, harmonic percentages that you see in various applications like 6 pulse, 12 pulse, 18 pulse, 24 pulse, electronic, lighting, PCs and VFDs. You can see that PCs are the largest contributors for harmonics, but when it comes to VFDs, this is what we typically see or generally see. So most in most of the applications, VFDs come with input reactor that is common, and we don't see such bad numbers as displayed here. So this is typical. And going to so before getting into seeing how installing input reactor changes THD, total harmonic distortion of current, I just want to back up a little into a bigger picture here, which is electrical distribution system. Well, I want to focus on generators. So I just wanted to have a discussion on how generators and VFDs go hand in hand. So, and and you should not be surprised to see planning for harmonics is one of the aspects that we consider while sizing the generators. So, in order to understand well, sizing the generators is one of the topics that we can look. That gives a very good perspective of how a generator and a VFD goes hand in hand. So going into the generator sizing, so briefly, we can look that this is a list of the items that we consider when we size a generator. And we can see that planning for harmonics is one of the important aspects that we consider, because our topic is VFD compatibility. So I'm focusing on VFDs right now. But this is a very good slide where we can have a brief look on what are the points that we consider for generator sizing. And I wanted to mention here, when considering generators, one of the important aspects is consideration of nonlinear loads. Most nonlinear loads have the characteristic of converting AC to DC. So this type of rectification will typically result in 35% of harmonic, 35% of current distortion. And we need a filter for that. So when we say filter, we see that filter is an important aspect here. So let's take a look how generator looks at a VFD. So VFD is seen as a rectifier by the generator. When sizing the generator, voltage and frequency transients are not an important issue, but we can see that harmonics are always present. So what we can consider VFD as is as a linear load. And when it comes to filtering, when we have a filtering for the drive to remove the harmonics, we can see that we need not to upsize or downsize or work with sizing the generator. But if the drive doesn't have any kind of filtration for harmonics, then we see that it typically needs to be like 2 to 4 times of the size of the motor being powered. So here I want to stress that we have to size the generator. So based on the filter requirement, here the point is harmonics. So if we have a good harmonic filtration, then we need not to size generator big. And 15% voltage dip tolerance impact the size requirements for any cross the line starting motors in the system. And coming to the main point here, 15% distortion tends to result in application issues. So we see that IEEE 519 have 10% voltage distortion as standard. So the voltage distortion is proportional to harmonic current and the source impedance of the alternator. This is the most important point that I want to focus on, because we can see that the distortion is directly proportional to the source impedance as well as the harmonic current. we have two solutions that we can propose. The first solution being having a good filtration device and or reducing source impedance, or in other words, it's just having a large alternator. We can also come across one more thing, where motors, if a motor is connected to the alternator, it is connected in parallel, so which reduces the impedance. But motor being small size, that consideration is not significant. So that's the reason we don't consider adding the motor's impedance in parallel as a significant thing. Moving on. So as I already discussed, so these are the ways that we can reduce the harmonics: active or passive filtering, and upsizing the alternator. And you can see that we are using typical rule of thumbs here, but rule of thumb analysis varies significantly with the type of non-linear device and the alternator's voltage configuration and general size range. So rule of thumb works generally, but we should be cautious of that. That's what we should be aware of. So we say that we need to have passive filters, right? So when we have passive filters, we should be worried about the leading power factor. So we can ask a question here: can standby generators handle leading power factor? Yes. And high levels of leading kVAR drive the generator excitation current to low values. That is an important point that I want to focus on. And this makes it difficult for the generator voltage regulator to control. So one of the good rule of thumbs that we use is VFD horsepower to be 50% or less than the alternator rated kW. If a horsepower is greater than this, then the calculation should be done and compared to the reactive capability curve. So moving on, hybrid filters. So this is the example where it shows we use a capacitor cutout contactor, which reduces the kVAR for the generator. So at this point, I want to turn this presentation to Steve again.
So question, is there any, with VFDs, is there more of a issue of voltage harmonics or current harmonics? And how does that make a difference?
Current harmonics are typically more, but not voltage harmonics. Does that answer your question, Sajid?
Yeah.
Cool.
Yeah, to add to that, usually it's the current harmonics going through an impedance that cause the voltage harmonics. And if an example would be a power plant that we did quite a few years ago, they had, I think, 8 or 12 200 horsepower cooling tower motors that were being fed by a dry type transformer. And as we started adding drive, so that they were running with basically reversing starters, because they run both forward and they de-ice and reverse. So drives are a great application because they could be able to save a lot of energy by reducing the load reducing the speed when it didn't need to be. As we added, the first drive was fine, the second drive was fine. By the time we started getting up to about 60% of the cooling tower being converted over to drives, we started seeing some very unusual disturbances in the system, and it was causing VFD failures. And we found that there was so much saturation, and this transformer that was feeding these was a dry type transformer. There was so much saturation that it was causing, well, obviously the voltage or the current harmonics were building until the voltage harmonics were exceeding well beyond 10%, maybe 15%, and that caused a considerable issue. So we typically, when we see a spec that says keep voltage distortion down below 5%, we rarely worry about that. But if you keep the current distortion down, you'll never get the voltage distortion. So I think you can see my slide here with a typical waveform. This waveform is actually discontinuous, which means
you need to share
that,
your screen again. Sorry.
oh, I'm sorry. Are we not sharing? Is that coming up
Okay.
now?
Yes.
Yes.
Oh, sorry.
We could see it now.
Okay, thank you. Okay, so this waveform is obviously discontinuous. In old days, I remember in schools with clock systems that were using the power line to synchronize off the 60 hertz. It actually caused clock problems to occur because of that discontinuity. This is more typical when you have a reactor. It smooths out a little bit. The previous one could be up to 100% or more distortion, meaning that more of the current's distorted than is fundamental 60 hertz. This is probably between 30 and 40%. I'm going to run through these very quickly. I wrote a white paper quite a few years ago, and Craig Hartman, our great PE engineer that passed away from leukemia a while back, updated this just I think a year or two ago, maybe a couple of years ago, where we went through a fairly extensive dissertation on harmonics, going through all the different ways you can mitigate harmonics with passive harmonic filters. Actually, back in '88, we received a patent for one of the early hybrid passive harmonic filters. And we thought that we would only have that technology valid for a few years until it was all using solid state electronics. And still today, most of our jobs are calling for passive filters because the expense is so much lower. But the other methods, 12 pulse, so these slides are basically showing the problems with multi-pulse applications when you have voltage imbalance. So theoretically, they're very, very good. But when you get voltage imbalance in real systems, it's more of a problem. If you would like more information on this, there's some very interesting things here, including one of these graphs here later on that shows the cost differences of different kinds of harmonic mitigating technology. If you send me an email, I'll be glad to send you a copy of that paper. I'm jumping right now to this is a job I think we just shipped and commissioned a couple of weeks ago, where this is a NEMA 3R irrigation. Actually, it's not irrigation. It's actually the domestic water out of a deep well turbine pump to a dairy. So it's all of their water for the plant. And when we first put in the VFD, it already came with an AC inductor in this section down here. So the VFD is it's actually a 500 horsepower. And we wanted to apply an active harmonic filter, which had usually been the most expensive type of harmonic mitigation, one that's starting to become very, very popular now. And again, that we've got graphs that kind of compare costs. So that again, the topology, we had this AC inductor here standard, and we applied this active harmonic filter, which we'll get into in a minute. And the way an active harmonic filter works, you may already be familiar like with the noise canceling headphones. It's basically injecting noise at 180 degrees of what noise is already there. So this noise, if you had the third in a single phase load, but the fifth, the seventh, the 11th, the typical non-triplet harmonics would be injected with current at 180 degrees phase shift. That looks like a pretty nasty waveform of noise you're injecting, but the result is you convert this into this. And I'm getting more and more sold on this technology for multiple reasons, but cost is not the lowest. So continue on. This shows you the outcome of what we went through a process to determine what is the best way to really make this system work. When we first put the system in our test lab, we have a generator. I think we loaded this up to about 300 and some amps. We were getting 49%, almost 50% distortion. And that's with that harmonic filter. Now, granted, we have a weak power source, so that might have been worse than normal. That's what the waveform looked like from a current standpoint. You don't see a lot of too much flat topping, even that's where you start seeing the flat topping, we call it, on the voltage when it starts getting bad. So we decided, well, we really need to add more impedance to this. When we started up the harmonic filter, and it injected its current, and this is a 100 amp harmonic filter, on a 600 amp VFD. This case, it was about a 300 amp load here. We were only getting the harmonics down to 24%, only dropping them in about half, which makes sense because we had so much to start with. So we added another DC inductor, which without the filter running brought us from 49% to 31%. And that made a huge difference in our filter performing where we expected it to perform, with an outcome of 6.5% current THD and this waveform, which is very acceptable. This particular utility said that you have to maintain less than 15% TDD, total demand distortion, or they don't penalize you, they turn you off, I guess, is what they do in this remote Idaho market. So that was a very interesting application. Sometimes actually these active harmonic devices can be the least expensive solution. Here you see a couple of units mounted on the wall. These are in parallel. So you got to remember the beauty about this is you're not putting all of that current in series. You're not having to process that whole 600 amps. We have 100 amps of injection here. And so if you have a lead lag, and a standby, you don't have harmonic filters on each of those. You've got one device, and we do a lot of those applications that make a lot of economic sense. Harmonic effects, I'm not going to spend time in that. I think you already are aware of some of the problems that can happen when the harmonics get too large. Clear back in '88, when we got, I guess the mid '80s, when we got a patent on this, harmonics were thought by most vendors to not be important. We had one individual at a university, Utah State University up in Logan, an engineer that was very ahead of his time. And he said, I don't want another drive coming into my facility that doesn't have some harmonic correction. And that was clear back in those early days. And so we started developing these, thinking that it was going to be short term, because we actually first started trying to develop a buck boost solid state top circuit, and decided that we had so much reactants, so many reactors in there that we just fell back to that as a quick solution. This is in that paper I talked about, which many people find very interesting, is if you take a buildup or a packaged VFD system that has a circuit breaker, maybe bypass, those kind of things, and that's a level of 100% with a standard AC reactor, a passive harmonic filter is about 150% from a cost standpoint. A 18 pulse drive is almost cost prohibitive at 5 times on a very small drive, as you can imagine, at that big 18 pulse phase shifting transformer. And then these other technologies in between. Now, again, you get the right application and the active harmonic filter can actually become very, very cost effective. But this compares your active front end, which is processing all of that power, and you also generate maybe a little bit more EMI RFI if you don't have a good filtering, so the filtering costs you more money. And so we kind of look at a couple of 3 levels. 0 would be no harmonic mitigating equipment. You're going to see 70 to 120%, depending on your source impedance. With AC and DC link reactors, 30 to 40%. That's a very cheap way to start. 12 pulse, some have gone to that. And theoretically, you can get to 12%, but any voltage imbalance, and you're right back up there. IEEE 519, of course, is 5% for the short circuit to load ratio that is the larger customer, all the way up to 20%, and the 8 and 12% in between. And then you've got passive hybrid harmonic filters, 18 pulse VFDs, active bridges, and active filters. And I think as Sid had indicated earlier, it's very, very popular to have these passive harmonic filters, but there are some consequences, like in generators, you are bringing in power factor with capacitive networks there. And if you have too much of that, that's going to be a challenge. So I apologize. I'm going to try to run through these slides of application considerations. And obviously you've seen tons of applications out there. Probably the most unique one I ever had was a customer called us up and said, can you use an inverter for a pig killing line? So we actually got enough impedance that the inverter could handle the shock to the pig, and they thought different frequencies actually were more effective in killing pigs in a slaughterhouse. But we don't do many of those applications. The first issue in applying drives is certainly that enclosure. And we just, for example, just got a project down at the LA Convention Center, and they didn't have any money. They wanted to just buy this chassis from us and a conduit adapter to make it a NEMA 1. And we said, well, we'll be glad to do that, but could we find a way to at least put that in an enclosure so that if you have issues down the road, you maybe need to replace the inverter, that at least you don't have to go back in that same footprint, because that's the challenge of replacing older drive systems is some are very narrow and tall, and the footprints cause a lot of challenges. And you can't add a reactor, you can't add an EMI or RFI filter or those kinds of things. This other one here is an 800 horsepower system, and you can't really see it very well, but the top is actually ducting that out outside the building. So that cool, dry, and clean are our models in that area for the electrical environment for enclosures. Lots of applications. I'm sure you're very familiar with constant torque versus variable torque and the things that you need to be concerned about in applying those, and even constant horsepower loads. This particular job, not a very good picture, but this is in a, we couldn't get a picture in the installation because it's in a classified area at Pearl Harbor for their submarine feedwater pumps. But they do have the active harmonic filter integrated into this package and a bypass system. And you can see it's air conditioned and it's an NEMA 4X. So that's an example of a package system. Another interesting application in conveyors, which is certainly constant torque, but when you're going downhill, now you've got regeneration. And there's a good place for either an active front end where it will regenerate that load, and you do have to worry about the harmonics from that standpoint. We had an application up in Alaska where they were loading wood chips into a ship, and they were running on a standby generator. So they had to have low harmonics, they had to have regeneration, they had to have control of the conveyor, and all of those added up to an obvious way for us to mitigate harmonics and meet the load demands. We've talked about the electrical environment. One thing I didn't really mention a lot, but the cable on the output of motors, you've seen probably manufacturers advertise don't install a VFD without a VFD rated cable. It's becoming more talked about. I haven't seen a lot of real issues where we do measure a lot, do a lot of ground resistance testing and measuring cables and commissioning. Another interesting thing, we just were called in as a consultant for a project in I guess it was the airport in Honolulu that was just completed for the baggage handling systems. And they had completed 2 before this. This third one, they actually used inverter duty rated cable because it was specified. And they had continual issues with DVDT failures, first turn winding failures. And they were using inverter duty motors. And we received a number of those motors, did root cause analysis on them, found that there really was a significant amount of DVDT. And the final conclusion, we were finished with our contract when we came up with what the issue was that was happening. But the motor manufacturer, which is a popular motor manufacturer, which it was an inverter duty motor, just said, all right, it's our fault. They're still under 1600 volts, which is what their calculation was. But I just found it interesting that the only difference between the first, the second, and then this third one was that they were using inverter duty cable, which might have had some complication, which we don't yet understand. Process control, this again is a lead lag type of system that you can get into redundancy and all kinds of things when you apply VFDs that you would want to put that together. And controls, the most common control obviously is a PID loop with a standard pressure controller. But this is for a potato processing plant where it's completely PLC controlled and tied back to like a SCADA system. I hope I'm not going too fast here, but when specifying VFDs, obviously that configuration, this is acceptable as a minimum standard to put on a wall, but there's lots of reasons to consider a packaged approach, and that's what we're really good at. Also, when you specify the features in a VFD, you've got software and hardware features. You've got the number of digital inputs or analog outputs or whatever. You're probably aware that there's almost no one that uses even 20% of all the parameters. There's over 500 parameters in most drives nowadays. And so just getting to the right ones is necessary. And also maintaining that those parameters are kept there from a long-term standpoint is necessary. Compatibility, I think we talked about most of all those issues. Commissioning, is obviously an important part of all projects, that you document that. There are specifications where they actually ask us to measure. We just did a medium voltage project with, I think, 3 1,000 horsepower medium voltage drives. And because they've had problems with other drive systems in the past, they asked us to, part of the commissioning process, to do vibration analysis and to do the bearing current and DVDT checks as part of that process. You've probably seen that you've got everyone and his brother sells drives nowadays. Like you can probably almost buy them, you can buy them from Walmart, actually, now. So when you do the commissioning, having an individual that knows something about arc flash and NFPA 70E and those kind of things is something we would recommend. And then the aftermarket support, we go to a great extent. We have, like I said, over 3,000 drives in stock, so we can usually take care of a customer, almost immediately to replace a drive. We have huge stocks of spare parts, and of course, field service engineers. And this last area of the service, this doesn't go real well as far as our clean, dry, and cool. This one over here, the customer asked why this drive failed. Well, we found all kinds of rat urine and droppings inside the drive on the circuit boards primarily. So that's pretty obvious. This is interesting when you think about it from an arc flash standpoint. We like to try to find a way where we can have our filters removable without opening the cabinet. That's not always possible, but that's a great way to do it. Also, in being able to monitor the fault codes and those kinds of things is an important thing, we think, in this second area of parameter checks. Jump through those. When we do preventive maintenance, you'd be surprised how often we find a loose connection. Some of them actually from a manufacturer on the manufacturer side of a reactor, load reactor, or something like that. One interesting thing we're doing for a large oil company now that's really made a big difference. It might go to this last area about this life cycle repair replace analysis, what we call our total electrical asset management program, is we're doing DC ripple checks on their DC bus of all the drives. We're finding some drives that could be 10 years old and have millivolts of ripple, and some that are 1 year old that are actually approaching 10 volts. And we're using that as a means of predicting, we want to avoid this failure. Here's a diode failure, typical diode failure. And we're finding that keeping that DC bus operating correctly is an important piece of it. So this total electrical asset management concept is where we'll go into a facility and we'll analyze, is the equipment current generation? Is it a legacy product? Is it obsolete? Are spare parts available? And we'll do an analysis with that customer with a future of, okay, does it make sense to replace the drive? For example, capacitors are one of the, I skipped over normal part replacement. Fans are the main mechanical device that you need to plan on replacing every so often. But manufacturers vary quite differently. Some would say, replace capacitors after 10 years. We've got many drives operating, into 20 years with no capacitor replacement. Allen Bradley in their literature would say you should replace the capacitors every 3 years. I found this life cycle repair replace program that we've done for our customers to be very valuable in really tuning in on what is the right time frame and frequency for the repair and replacement. So I know that we've gone past our question time, and I don't see other questions, but I'm hoping that maybe we'll get a couple that might have piqued your interest.
Okay, I can start with one.
Okay.
So have you come across any package unit where you package a VFD and a UPS system together, where you charge the batteries from the DC bus of the VFD, and during power loss, use that DC power to convert back to AC? Yeah, so we had this issue in one of our projects where we did not have enough space available on an existing substation, and client wanted to have new VFD UPS system for ID fans, and they had unreliable power system. So I don't know if you guys ever came across any such application where you can combine those two together.
Let's see if I can unshare my screen here. In medium voltage drives, we're finding that they're almost standard with little UPSs for the control side of the circuits, which are very inexpensive and doesn't cost them but a few $100s if they do a double redundant online type, maybe a little bit more. And so that's quite frequent to have a UPS system backing up the control power. A lot of drives nowadays, not all of them, but they take their control power off the DC bus. So there's a lot more ride through than there used to be when it was just strictly an AC arrangement. But I've never seen taking the DC bus to charge the UPS system, because now you're talking about probably wanting to have more ride through on the power side if you really go to that extent. And I've usually seen the addition of capacitor banks if the idea is getting more ride through. And of course, the other things are being able to be compatible to start into spinning loads and those types of things. So no, I've not seen specifically taking the DC bus, and it probably has to do with a UL component too, that there would be very few UL 508A or UL 508 UPSs that I know that would allow us to bring a DC bus directly in from a drive for that purpose. That may be a limitation, but technically your question is valid. It could be done. You just have to make sure you got good voltage regulation for what they're looking for. We do have drives that are usually in third world countries. It's very popular to have a drive that runs off of solar. They call them solar drives, and they have very wide ranges of voltage tolerance.
Okay, yeah, that's good to know. Actually, this project was in Middle East, so they have enough solar capacity there.
Okay, right. Yeah, there's it's become very popular in the solar applications.
Okay, that's good to know. Thank you.
Did we have one question? Go ahead and give that to me.
Yeah, I have one comment from Mr. Matsuda again. He said, while passive filters are low cost, their LC component is fixed, usually tuned to 100% speed of BFD / motor. Active harmonic filters are higher cost, but they mitigate harmonics through all loading by or speed combinations and provide power factor correction.
Okay, good question. And I think that I understand some of what he's looking at there. Truly, an active harmonic filter does cover the load range very effectively. Obviously, in the very lowest ranges, you've got a little bit of losses with fans and those kinds of things, but you're only injecting the amount of current that you need, and they're very, very efficient. We find that passive filters are also quite efficient with the reactors, but the earliest ones were strictly shunt tune filters for the fifth harmonic, maybe the fifth and the seventh. And those definitely had a lot more of the problem of not doing well at other light loads. We find that in the range that drives operate, typically 50% to 100% power, that the current generations of harmonic filters, passive harmonic filters, do a real good job of a pretty broad mitigation over a broad range. And there was one of those graphs in there that showed that all the way. Matter of fact, I wonder if I can grab that real quick. You have to. Okay, let's see if I can share my screen. I'm lost my cursor. Which of my screens am I sharing now?
I don't see any of your screen.
Okay, I don't see the ability to share my screen now, so I'll, in that paper that we wrote, there's a graph that shows what I'm looking at now with the various voltage imbalances of 1% to 3% and a load range of 0 to 100%. And this, what is called more of a hybrid filter, actually has a fairly not linear performance in this graph of showing from just below 40%, maybe 35%, all the way up to 100% in the testing, a very high level of mitigation that's flat rather than linear. So that's what I was referring to
Yeah,
that on that.
I'll take few more questions quickly. One is from Tony Akayan. He's saying, are 12-pulse VFDs being phased out?
I'm sorry, I didn't understand the question.
Are 12-pulse VFDs being phased out?
Oh, are 12 pulse 50s being phased out? Great question. I thought for a time that they were. There's been a couple of manufacturers that build their diode bridges in a dual bridge. And from those manufacturers, there's every so often it shows up that someone is accepting a 12 pulse type of arrangement. If you had to actually go find a manufacturer that is really big in that industry, it's not certainly prevalent, and because the harmonic mitigation is usually requiring something lower than that, we've seen greatly the fall off over the last 10 years ago. It was probably one of the at least top 3 mitigation techniques. Now I probably don't see it 1 out of 10 times, maybe 1 out of 20 times.
Okay. Another question from Sharjil. Data is for a system with standby generator, which harmonic mitigation system is the best? Passive, active, AFE, due to the possibility of different source impedances.
Okay. Based on, I guess my answer would be from a standby generator standpoint, all of those work, and we've seen all of them be effective. Passive is still the least expensive, and it's almost become commonplace because of the number of problems that there'll be a question asked, do you have a generator? And if you do, there will be a high desire to specify cutout contactors so that you're getting the load up into that range before you bring in the capacitors that won't cause generator issues from leading power factor. So I wouldn't say that passive filters are not being used in that regard. Active front ends are, you're talking about 4 or 5% current THD. So as long as the filter for the high order harmonics is done well, there'd be no issue using that. That's probably the most expensive. We would typically think of that as maybe being 3 times the cost of a normal 6-pulse drive. And the AFE would be a great solution, particularly if you have multiple motors where the current needs of harmonic injection work out well to your benefit. If you have, let's say, all huge 800 horsepower, or you probably won't have that in low voltage very often, but maybe 500 horsepower, if you had, say, 5 of those, I would almost suggest that we still see a need for 18 pulse drives because they're more cost effective than the active front ends and the active harmonic filters in an application like that. Does that help a little bit with that?
I want to comment here too. So
Go ahead,
using
Sid.
hybrid filters is the best solution as I can think of when compared to passive, active, or AFE.
I didn't want to sound biased, but we're finding that it's more and more you cover a lot of errors because you just add another module and inject more. You don't have to redo the whole power structure.
Yeah,
is that screen being shared now? Can you see that
Yes.
hybrid filter?
Yeah, we can see it now.
That's what I was talking about. And again, if you're more interested in that, then certainly send me an email and I'll send you that whole paper.
I'll take 2 more quick questions here. First one is from Nick Rosner. He says, so continuing from the last point, right? So for passive filtration as the most effective solution at low horsepower ranges with drives operating as low as 30% for variable torque loads. I think he's asking, is passive filtration is the most effective solution?
Yeah, you just saw that graph that I put up, it showed that that's about where it starts tailing off.
Mm-hmm.
But again, think about when you're down at 30% load, your current is a fraction of that rating, that motor rating. And so you're not really adding a lot of current harmonics to the system. You just need to worry about, are you actually getting down to the loads where you're now, for example, we used to sell tons of these passive filters, the original one that we patented back in the 80s, which has been improved on a lot now, in the oil field. And every well in the area was getting these, and the utility started seeing at their distribution centers leading power factor and started having problems because of that. Just so many small drives that were out there that were single units. So we typically see that as the most cost effective until you can have, let's say, 5 of those 30 horsepower or an MCC full of those units, and then add one active harmonic filter and don't have to have all those individual filters. That's kind of how I'd look at it. We would look at it on a case by case basis, because we've effectively used all mitigating techniques, including external phase shifting.
Okay, and last question from Mr. Higgins is, when does a harmonic study, system study is required? Is there any certain size or quantity around which you should start doing harmonic study? I think it depends on number of loads you have, which can create harmonics.
Yes, that's certainly a subjective question. The universities that back in the 80s and 90s were not worried at all about harmonics, they're now all of a sudden adding active harmonic filters because those drive systems have already gone in. The problems now manifest itself, and so they're finding ways to go back. And I kind of look at it, you can either clean up the effluent into the lake, or you can dredge the lake later, and it's usually better to try to plan that in your original engineering.